And hello everyone, a little bit of correction before I go on. I kept saying last video that dBE_dRE is equals to dBE_dP. Okay? Yeah, dBE_dP times dt. Okay. Okay, I think this part's actually correct, so let me take that out. Okay. Yeah. Okay, so the equation that I kind of realized was wrong was this one, where I started differentiating dBE_dRE. I tried to put the friction factor and Reynolds number on the right hand side. Okay, what I forgot was to include this factor of 32 over 4L over D cubed. Okay, this one is important when I differentiate both sides with respect to Reynolds number. Okay, and I assume that of course L over D is constant, and of course 32 is obviously a constant. Yeah, but L over D is constant when Reynolds number change, because the only thing that causes Reynolds number to change here in this case is the fluid velocity or fluid state. Okay, temperature, whatever, that should not change for L over D cubed. Okay, so that's the correction I want to make before I continue. So I'm going to add this, and of course corrected coefficient in front of dBE_dRE. Okay, so I'm going to commit this to GitHub, sync the changes. Okay, don't run git fetch. Yes. Okay, so that's the kind of it for the pipe theory. Spent extensive time deriving this. Okay, so now let's say we have all the derivatives done. Okay, how are we going to start testing it? Okay, so there are two ways. There are two ways you have to test this. So first things first is that okay, we need a way to test this, right? We need a way to test this fanning friction factor. We need to make sure if we supply a Reynolds number, we should be able to get the correct fanning friction factor. Okay, so that's one. So if this is actually correct, if this function that returns us the fanning friction factor is correct, then after that, yes, we can differentiate this function using a numerical library or an in-house derivative. So once that is done, yeah, I can sort of have a baseline check for what this derivative dF_dRE is. Okay, I can have some sort of baseline check. Okay, once I have dF_dRE, okay, or at least where is it? Okay, let me use the keyboard. Yeah, once I have a dF_dRE, what do I do? Okay, hold on. Yeah, once I have a dF_dRE, yes, I can actually use that as a basis of, you know, calculating dBE_dRE. Of course, I can use that to calculate dBE_dRE. Okay. Yeah, I have a dF_d. Hold on, let me check. Hold on. Ooh. Yes. Okay. I have a dF_dRE right here, which I can use to calculate derivatives. Yeah, I can use the dF_dRE to calculate, yeah, dF_dRE here, obviously. And then I have this RE square here, and my whole function here is just to help me return. Okay, my whole function here is to help me return dF_RE times RE squared, everything together. Okay, so okay, let me type that out. It's way better. Okay. So it's a multi-step process and we'll need testing. So let's say we have a function that returns the value of, okay, fraction d by d Reynolds number. I'll put in brackets. Then you have the f fanning times re squared. Alright, so that's the function that's supposed to return. Okay, so the function is supposed to return this value, d by d re of this much. Okay, we can verify this by using, okay, so I'm going to do some manipulation again. Oopsie. Let me yank in the dollar signs and I'll paste it here. Paste it here. Okay. Oh. Alright, so I have this equation. What can I do? I'll use the product rule here. Okay, so I have re squared times fraction the f fanning the re. So that's the first term of the product rule. Then I'll have the second term as well. So I need to plus okay, the re squared, the re is just equals to 2re, 2 times the Reynolds number because I'm differentiating this side. Then I'll have the fanning friction factor, F fanning. Okay, 2re times F fanning. So the F, the re can be done numerically. Okay, so I have this value, yank it, paste it here, use the Vim paste. Okay. Okay, can be calculated numerically, whereas okay, okay, this can be calculated numerically, whereas okay, the first term here, yank it 5 down paste, is calculated analytically. So I will need the values. Okay, so this is actually a unit test first, yeah? Unit test 1, 2, 3, 4, 5. Unit test of derivatives. Okay, so I will need this. Yeah, I will need the yeah, I will need the what do I need? The F, the I'll need the fanning friction factor, F fanning, and Reynolds number, and substitute into the above equation. Then I will have a numerical reference. Okay, and I'll have some kind of numerical reference for this value right here. Okay. So then I can use the analytical reference on the left hand side. Okay, to compare it. Okay, I have a numerical reference to compare the left hand side with. Okay, so that's the idea. So after this unit test is done, I will of course want to no, what was I doing here? Okay, this is, I think, integration testing. Okay, better don't use the word integration. Okay, this is not unit test anymore. Okay, I think I better use the word integration, but in the computer science sense, not calculus. So I have to make that distinction right there. So after so I'm going to check for mass flow rate given a pressure drop. List of friction. Okay, hold on. Let me read through this. I'll get back to you. Okay, so I think this one wasn't actually testing the derivative, but yeah, I was trying to test the Churchill correlation. So I think I better change the what do you call that? Let me go up. Shift C. Testing the Churchill correlation. How to make sure it's accurate. Okay, so that's the Churchill correlation. And the Churchill correlation is just here to provide us the fanning friction factor. Okay, so this is important because you want to test it. So, okay, so what was the... Alright, I kind of changed my methodology here. Okay, so I have a mass flow rate given a pressure drop. Okay, so yeah, just the first part. The first part is to test for the friction factor using the Reynolds number. So this is the simplest test ever. So assuming there is a fixed, I mean, every Reynolds number will correspond to a unique value of a friction factor. Okay, every Reynolds number will correspond to a unique value of friction factor. Meaning to say, if you look at this chart, if I have one Reynolds number, I will only have one friction factor. Okay, so that means that the friction factor is a function of the Reynolds number. Okay, so that's the first kind of test I want to do. Second is to supply a friction factor and extract a Reynolds number in return. Originally, I thought, okay, this was one of the ways, but that's very problematic because Moody charts have two values of Reynolds number for a single value of friction factor. This will happen for a Reynolds number less than 10,000, for example. Okay, so the first test will be okay. So maybe, but the second test will be problematic. So to modify, maybe test 2. Okay, modify test 2. Test 2. Convert. So I'll convert the Moody chart to a Bijon number versus Reynolds number chart. So what do I mean? It is basically it's like this. So I want to have an equation like this: F Reynolds number times Reynolds number square equals to 32 Bijon number over all of these things, and I want to set that sort of equals to 0. Yeah, so I want to set this equation equals to 0. Okay, so to modify test 2, convert the Moody chart to a Bijon number versus Reynolds number chart. See if this number corresponds to... Oh, that's... Yeah, I don't want to use this. Okay, so to modify test 2... okay, so here's the idea. Okay, to modify test 2, because of this problem, I will just convert the Churchill equation to a Bijon number versus Reynolds number equation. Okay, that will be, yeah, that will be something like what we've seen before. Okay, so how do we then obtain the Bijon number? We can use a 1D Newton-Raphson method to suffice. Okay, so we will just need to supply, oh yeah, this is what the equation will look like. For the Newton-Raphson method here, we will need to supply a Bijon number and a given 4L/D value, right? And of course, supply in the F Reynolds number. So this Newton-Raphson method F, which will be substituted in here, will be this whole value here, and this is supposed to be set to 0 as far as possible. Okay, and then we keep iterating on until we find the root, and that will be sort of our Newton-Raphson method. That we can go backwards and forwards. We can use Reynolds number to find a friction factor, or we can use a Bijon number to find the Reynolds number. Okay, so that is the idea. Moving on, so there's a test series 1. For every test, we have a reference and a test result with which we compare. The reference should be quite easy and intuitive to see if that is correct. The fanning friction factor from Churchill's relation is quite easily calculated, as it is explicitly in terms of Reynolds number and roughness ratios. So what's the test series 1? Test series 1 is actually calculating F from RE. Okay, so F is the fanning. Okay, calculating fanning friction factor from RE. So what's the reference? We can actually look at the roughness, the Moody chart. Okay, we can look at the Moody chart here. Okay, but that was a bit difficult if I want to keep reading the Moody chart. So I use the online Darcy friction factor, or online fanning friction factor calculator. So this is some omnicalculator.com, or I can use this. Let me use a nicer one. Okay, something like this, or engineering toolbox. I think I use engineering toolbox. This is quite a, yes, Colebrook equation. So this is what I used. Okay. Okay. This is what I used. Okay. Actually, I used this, the engineering toolbox. Is it? Okay, to help me calculate the reference. So don't know whether it's accurate, but yeah, I use engineering toolbox to help me calculate the reference values with which to test the fanning friction factor. And what did I do? Yeah, I looked at the curve, the Moody chart, as a sanity check. Okay, so like to do sanity checks, meaning to say make sure that the calculator is doing something roughly in the correct region. So I'm making assumptions that this Moody chart here is actually correct, and this thing here is also pretty correct. Okay, so this is a Colebrook online calculator. So this is, I think, is this the fanning friction factor, or what friction factor? Oh, this is the Darcy-Weisbach friction factor coefficient. Yeah, so they say here is the Darcy equation, Darcy friction factor. So oftentimes you got to be very sure which friction factor it is. Okay, so this is the Darcy friction factor or Moody friction factor. They are pretty much the same thing. Okay, so what I will do is that, okay, let's say I will try to read off the graph a point that is pretty easy to read. So for example, over here, 0.05, yeah, fanning friction or the Darcy friction factor here, 0.05, it has a surface roughness of 2, Reynolds number of maybe 10 to the 7 here, right? 10 to the 7, you will have a relative roughness of 0.02, and the friction factor we expect is close to 0.05. Okay, that's expected for turbulence. So I will pick points like these. They are easy to read off the graph. Okay, next thing I do is I plug it in here. So for example, what hydraulic diameter, okay, let me just put 1 and then I'll just put 0.02, 0.02, and then what's the Reynolds number? I just put 10 to the 7, 1E7. Let's calculate, see? And based on this, the friction factor coefficient lambda is 0.0485, and then this is very close to 0.05 as you can see here, and the roughness ratio is 0.02. Now this is a point I can say, okay, pretty safe, this is a good reference point, and I started using all of these points as my reference point. At the same time, I also look at laminar flow. Laminar flow, very simple, we have 16 over Reynolds number as the analytical solution. I mean for flow in a laminar region, you should have 16 over RE for your fanning friction factor. So that'll be the reference fanning friction factor. Everything else I will have to start looking at the Moody chart and then calculate point by point. Okay, so I'll put some in the smooth pipe region. I'll put some in the full turbulence region, so to speak. Okay, so this is the test series 1. Test series 2 is to calculate Reynolds number from Bijon number, not the friction factor. Okay. So for this testing, it'd be prudent to compare the analytical derivation to the new Okay, as I read this paragraph, this looks like actually the derivative testing. So let me okay, let me take this out. Okay, so I'll have a section saying testing the Churchill correlation first. Okay, and then I'll have another section called testing the derivative. Now that's a better organization. Okay, so I have the first part. Important is that important thing is for me to test the Churchill correlation first, how to make sure it's accurate. That's the first part. Okay, so calculate RE from BE. I will probably need a root finder algorithm. So either use my own Newton-Raphson root finding algorithm. Okay, so this is to find this. Okay, yank this and I'll paste it at the bottom here. So I'll put this Newton-Raphson finding algorithm. Where is it? Yeah, I will use this. Okay, I'll put it here. 15 open. Okay, just to give it some space. Okay, so this is the Newton-Raphson method, which I want to paste it here. Okay, fraction 1 over, I'll paste this here, and yeah, so this is the Newton-Raphson method, the bare minimum of Newton-Raphson method. Okay, and I keep iterating till it's done. Okay, keep iterating till it's done. Okay, so yeah, so this is how I will do the Newton-Raphson method thingy, or use an external library. Okay, the external library to use usually is math.numerics from NuGet. Okay, so this is the C# way of doing things. So yeah, so testing the derivatives. Okay, I already explained how to test the derivatives. Okay, so yes, so let's see. Wow. Okay, I just delete all the text. It's actually confusing me more than helping me. So we have a function that returns this. This is the analytical function. We can calculate this side numerically. So for the numerical derivatives, we can use an external library or an internal library of for our derivatives. Okay, so how are these derivatives going to be done? Can be done using central difference or whatever. So I will cover those things in another video. Okay, so that's it for this video. I'll see you next time.